Let's try and understand exothermic and endothermic reaction with help of an example. Now the example is hydrazine gas reacting with hydrogen gas to give 2 moles of ammonia gas, and delta reaction enthalpy is minus 184 kg. Minus 184 kg itself means it's an exothermic reaction, it's giving out heat. Now let's understand few parameters. Now in this case, this is HR as we had seen earlier. Enthalpy of reactant climbs the hill, comes down and forms product. Alright, now this we already had seen was activation energy. For this reaction to occur, it has to cross this uphill. Alright, now it does cross uphill, but after that what happens is the HP comes much below over here. Alright, HR, the enthalpy of reactant was here higher, whereas enthalpy of product was lower, owing to which this became an exothermic reaction. Now this is the difference. Now if I take it, extrapolate it over here, this is what is for enthalpy of reactant and this is what is enthalpy of product. So this difference is del H, and since this is lesser and this is higher, so the difference is negative, and that minus del H is minus 184 kilojoule. That's what it is giving out. Now let's get a little more intense. Now see, forward reaction. Now how can you say that forward reaction is preferred here via this graph? From here, now forward reaction is this, and if I say backward reaction, that is 2 ammonia molecules giving back hydrazine and hydrogen, that's the back reaction, that is ammonia crossing the uphill and giving back hydrazine and hydrogen. So this is backward reaction. Now one thing let me clarify over here. Del H you find is the same in both the cases. So whether the reaction be forward or be backward, magnitude of del H would be the same, 184. Only the thing is here it would be plus 184, whereas here, because here this would become product, this would become HP and this would become HR. So owing to which this would become plus 184 kilojoule. I hope you understood. Now this is our reactant when we are going backward. Ammonia is our reactant and ammonia is our reactant and product is our hydrazine and hydrogen. So this is HP for backward reaction and this is HR. So the difference will be HP greater than HR for reversible for backward reaction. Therefore it is plus 184 kg, but the magnitude would be the same. Alright, so this part is, I presume, understood. Now we were talking about which path is favored, forward or backward. For that we have got to check activation energy. Now see, it starts from here in case of forward reaction. So activation energy starts from here to the peak. Whereas in this case for backward reaction it starts from here. So activation energy begins from this to peak. So obviously we observe that activation energy for reverse reaction is much more than activation energy for forward reaction. Alright, so activation energy for forward reaction is lesser than that of activation energy of reverse reaction, owing to which forward reaction is preferred. Alright, so forward reaction preferred because activation energy of forward reaction is much lesser than activation energy of reverse reaction. Alright, now forward, this I explained you, forward is minus 184 kJ and backward is plus 184 kJ. Alright, this already I explained you. Now product ammonia is stabler. Why do you say that product ammonia is stabler than hydrazine? Obviously because we find that the product that forms, it already has lost minus 184 kg, and it has come down here. So this product is more stable than this. Stability of this is much lower. Why? Because energy in this is much higher than energy in case of ammonia. This is the energy that ammonia possesses. Less energy, more stable. Reactant possesses more energy, so less stable. Alright, so these are three facts which you have got to keep in mind, and these facts are better understood via this graph. Alright, okay, now let's move on to enthalpy. Let's read this out. Enthalpy change required to break particular covalent bond in 1 mole of gaseous molecule to produce gaseous atoms is called bond enthalpy. With the help of example, I have shown all about this bond enthalpy. Okay. Now, for polyatomic molecules, for a particular bond type, average bond enthalpy is considered. Alright. Now, when we say average is considered, that itself means that there is some mystery behind it. Yes. Let's try and understand the mystery taking example of water. Water, we know 104 degree sp3 hybridization, 2 lone pairs, owing to which the bond angle is 104, that is owing to VSEPR, valence electron pair repulsion. So how do you, any subject, how do you make it better? So whenever you're talking about water, see how I spoke about water, all the properties of water, which is not required over here, but still I spoke. So you are also supposed to, whenever such molecule comes, which has a background there, which may be in physics or in chemistry, just try to recap those background. That helps you to solidify your substance. Anyways, let's progress. Now this is water. You have OH, OH, identical covalent bond. But see, what happens in step 1, we have cleaved this bond. Alright, now check out the del R enthalpy, 499 kilojoules. But then when it goes for the second one, it is 428 kg. Alright, both are endothermic. Alright, that's one thing which we know. Now, alright, so average bond enthalpy. So average bond enthalpy would be what? When we check out average bond enthalpy, it would be both added and divided by 2, of course. So it comes to 463. So it comes to 463.5 kilojoules. Alright, so this is how. So we normally, like for example, if I take methane, CH4. So there are 4 CH bonds. Alright, now those 4 CH bonds, every bond will have slightly different kilojoules as its enthalpy. Alright, so what we have got to do is we have got to sum up all those 4 CH bond enthalpies and then divide it by 4 or get the average of it. So now for polyatomic molecules, for a particular bond type, average bond enthalpy is considered. Alright, so CH4, so CH, 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 4 bonds, different enthalpies, bond enthalpies, summed up and averaged. That's what is it. So anything got clarified? That when we talk about bond energy, does not mean CH, 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 all of them would be identical. Bond enthalpy, it would be different, and we have got to take out average. Fine. Okay.